Hello and welcome. In this video, we are going to be applying what we learned in 2.5 about implicit differentiation to word problems in context that we like to call related rate problems. And the idea here is that when we're talking about something three-dimensional or something in the world, it's not very common for only one thing to be changing at a time. So for example, say I was blowing up a balloon with air, and let's pretend that we live in a perfect world where this balloon is exactly a sphere. As I inflate it with air, a lot of different things are changing all at the same time. The volume is changing, the radius is changing, the surface area is expanding, if you're thinking about the rubber. And so all of these different things are changing with respect to time, so we could analyze their different rates separately. And that's the idea in this section. So before we jump into the word problems and the best approaches to thinking about them, let's tie this idea to taking the derivative with respect to t, because our variable of choice today is going to be t for time. So if we take the derivative of this expression just like we did in the previous video, but with respect to t, neither of these variables have a t. So when I take the derivative of 3x with respect to t, I get 3 dx dt. And when I take the derivative of y with respect to t, I get dy dt. And when I take the derivative of a constant, no matter what, I get 0. So each of these separate things, dx dt and dy dt, are really just talking about their rate of change with respect to time. So dx dt is the rate of change of x with respect to time. And dy dt is the rate of change of y with respect to time. So if we look at this equation, 3 times dx dt plus dy dt equals 0, I could solve this equation anytime I know either what dx dt is or what dy dt is. So over here we're being told at what rate is x changing. That means what we want is dx dt. If dy dt, if the rate of change of y is 3. So we're just going to take 3 and plug it in to this equation. So 3 times dx dt, that's what we're trying to find, plus dy dt is 3 equals 0. And then if we solved this, we would get that dx dt must be equal to -1 if this equation is going to work out. Why don't you go ahead and pause the video and try and work through the one right below this on your own. So hopefully you have had time to pause the video. We are being asked for the rate of change of y, so now we want dy dt, when the rate of change of x is 9. So now we're saying 3 times dx dt, which is 9, plus dy dt is equal to 0, and this is going to work when dy dt is -27. So the idea, you're going to have a differential equation, or you're going to have an equation that has derivatives with respect to time, and you're going to be plugging in certain things to find different quantities. That's the whole concept of what we're doing in this section. So let's talk about some strategies for dissecting the word problem and really working your way into it, and then let's work through some sample problems. So our ultimate goal in the types of problems that we're going to be working on in related rates problems, or the types of problems in this section, is that we are going to be looking at multiple types of rates of change happening with respect to different things, but our focus is going to be with respect to time. Every time you start one of these problems, I recommend that you first draw a picture of what is going on, or if there's already a picture there, add on to the picture, and list all of your given information off to the left-hand side of the problem. Remember that when you're working through these things, work from the left side to the right side, because you are writing up your math for a reader to follow your work. And if it's all over the place, it makes it really difficult for anybody looking at your work to figure out what's going on. So step 1, draw a picture. Step 2, write down any given information and what we're trying to find. So read through the problem and write everything down that you know or that you're trying to find from the problem right underneath your picture. And that's sort of your whole given section. The next thing you're going to do is, based on the type of problem, you're going to identify some other formula or equation, surface area, volume, Pythagorean theorem, something else that ties the variables that you're looking for together. And then you're going to plug in anything that is always true. So if a quantity is constant, you can plug that in. Otherwise, You're then going to take the derivative of both sides with respect to t. You're going to solve for whatever you were supposed to be solving for, and you're going to make sure you write your final answer in a sentence with respect to answering the question the problem was asking. So let's actually look through these steps in relation to a problem. Number 1, given a 10-foot ladder is moving down a wall. So here I'm going to draw my ladder. It's leaning against my wall over here. The ladder is 10 feet long. That is a constant length, so I can put that in my picture. It doesn't say the ladder is expanding or condensing or anything. When the ladder is 8 feet from the wall, so now we're talking about at a specific moment, the ladder is 8 feet from the wall. So I need some variables here. So I'm going to call the wall height y and the x, the length between the bottom of the ladder and the wall, I'm going to call that x. So when the ladder is 8 feet from the wall, that's talking about x. It is moving at a rate, so the rate with respect to x, of 4 feet per second. And the question is asking us how fast, so what we want, is the ladder moving down the wall. And down the wall is with respect to y, so we want dy dt. So I read through the problem, I drew my picture, identified all the information I could, and wrote it all over here. This is all given information. Now, in order to proceed with this problem, I need to come up with some formula that ties together the things I need, x and y and 10. And when I see this, this looks like a right triangle, which makes me think the most basic way I can relate the sides of a right triangle is by using the Pythagorean theorem. Now, nothing, x and y are not constant. They are changing. The length of the wall, or the portion of the wall we're looking at, or the distance from the ladder to the wall is changing as it moves. So I can't put anything in here. So the next thing I'm going to do is take the derivative with respect to time. So that's going to give me 2x times dx dt plus 2y times dy dt, and the derivative of any constant is 0. And now I'm going to plug in what I know to be true at this moment. So this equation that we just found always works. At this moment, we're looking for a particular value, so we can plug in what we know to be true at this moment. So at this moment, we know that x is 4, and we know that dx dt is 8. We don't know what y is, and we know that what we're supposed to find is dy dt. So I want you to think about the only piece of information we're missing in order to solve this problem is dy dt. Sorry, the only piece of information we're missing in order to solve this problem is y. Is there a way that we could find y at this exact moment when x is 8 and the hypotenuse of this triangle is 10? Sure, we can just do the Pythagorean theorem for this specific situation. 10 squared equals 8 squared plus y squared. That's going to end up giving you that y is 6. And now I just need to solve for the variable that I'm looking for. So dy dt, if I multiply 2 times 4 times 8, that's going to give me 16 times 4, 64. And I'm subtracting that on both sides. And I'm going to divide that by 2 times 6, so divide that by 12. So this is going to give me negative 16 over 3. So the next thing I'm asking myself is, does this answer actually make sense? Should this rate be negative? Well, yeah, that makes sense. I'm moving down the wall, so it does make sense that this rate is negative. So to answer my question, I'm going to say, at this moment, and I can say that because I defined on the left what this moment is. At this moment, the rate the ladder is moving at is negative 16 over 3, and our units here were feet per second. Now, if you said the rate the ladder is moving down the wall, then your rate would need to be positive. Otherwise, you're saying down and it's negative. That's a whole double negative situation, which doesn't work. So be careful with the way that you write your sentence. Make sure you're not contradicting what you're saying. This sentence should either read the rate of the ladder is negative 16 over 3 feet per second, or the rate that the ladder is moving down the wall is 16 over 3 feet per second. All right, number 2. We're drawing a picture. A cube is expanding somehow. How long will the sides be when the surface area is expanding at the same rate as the volume? So I'm going to pick x to be the length of my sides. This is asking me for x. We want x. How long will the sides be? And the moment they're saying is the surface area is expanding, so it's changing, which means not just the surface area, but the rate of change of the surface area, is equal to the rate of change of the volume. And the other piece of information they're giving us is that the rate of change of the legs, which in this case would be dx dt, is 1. So we're talking about surface area and volume. So I know that the surface area of a cube is the area of one side times 6, because there are 6 sides, so 6x squared. I know that the volume of a cube is base times width times height, which is going to be x to the 3rd power. So everything is changing here, so I'm going to take the derivative of both of these equations with respect to t. So dsa dt is going to be 12x dx dt, and dv dt is going to be 3x squared dx dt. Now we are being asked specifically about the moment where these two things are equal. So I'm going to set this equal to this. So 3x squared times dx dt equals 12x times dx dt. We know that dx dt is 1, or we could just divide it out on both sides. So we get 3x squared equals 12x, or 3x squared minus 12x equals 0. And if we solve this, we're going to get that x is equal to 0 or 4. Now 0 doesn't make sense in context of this problem. I can't have a cube if it has a side length of 0. So the answer here is 4 miles. But you would need to write out a sentence, which I don't have room to do. So I'm going to just say what the sentence would be. At this moment, the length of each side of the cube would be 4 miles. So make sure that your sentence answers the question that was being asked at the beginning of the problem. Let's work through a few more examples. Before we jump into number 3, I need to give Mr. O'Hare credit for coming up with this problem, because I did not come up with it, and its cleverness. He deserves some recognition, even though he's not at Doherty anymore. So this problem is about a football, and it's basically about Deflategate, about deflating the football. So yeah, it's hating on Tom Brady a little bit here, but that's okay. A football is roughly an ellipsoid, so you can just picture, and don't judge my inability to draw three-dimensionally too much. I have a football here, and its volume can be represented using this equation here, where A and B and C are all different radii that are just being formed in the different ways of this football. Say that the football is pretty rigid from tip to tip, meaning that it's not really changing its dimensions, and that A is equal to 11 no matter what. So all the time, the A radii is 11. Tom Brady is trying to deflate the footballs just enough to win some games. As the football deflates, so at the moment we care about, we're being told that B and C are roughly the same. We're being asked for the rate of change of the volume at the moment when B is 3.1 and dB dt is decreasing, so negative 0.1 inches per second. So looking over this, I've identified all of the given information. Now I need a formula that ties them together. And the nice thing about this problem is they actually gave us a formula to begin with, 4/3 times pi times ABC. Before I take the derivative, I want to plug in anything that doesn't change. So I know that A is 11. So if I plug that in, if I multiply the 11 times the 4/3, I'm going to get 44 over 3. And I'm going to go ahead and put pi there. And I know that B and C are the same, so I can just substitute in B squared. So the volume is 44 pi over 3 times B squared. Now I can take the derivative with respect to time. That's going to give me dV dt equals, if I drop the 2 down, 2 times 44 is 88, pi over 3 times B times dB dt. Now, this is what I'm trying to solve for. Do I have everything else I need? I know what B is. I know what dB dt is. So I can just substitute those values in. So 88 pi over 3 times B, which is 3.1, times negative 0.1, which is our dB dt. And this you are more than welcome to do on a calculator. I would like you to leave your final answer in terms of pi, so negative 682 over 75 pi. Or if you got some other decimal place, that's fine. Just leave it in terms of pi. So my final answer at this moment, the rate of change of the football the rate of change of the volume of the football is negative 682 over 75 pi, and the units here would be inches cubed per second since we're talking about volume. And if you need help working with your calculator, just let me know. I'd be happy to support you on that as well. What I'm going to encourage you to do, and I'm going to create more space here, is to go ahead and draw a picture for number 4 and 5 and identify your given information, and then unpause the video and see how you did just on that part, and then we'll work through the rest after. So hopefully you had time to draw your pictures and you can check and see that we have similar pictures with the same given information. So a cone-shaped paper cup is being filled at a water cooler. The procrastinator filling up the cup wants to make this break last as long as possible, so he's filling the cup slowly at a constant rate of 0.01 cubic inches per second. The radius of the cup is roughly equal to 1/3 of the cup's height. So both of those pieces of information are here. At what rate is the height of the water changing? So we want dH dt when h is equal to 2. So using this information, we're being given information about the volume. So it's likely that we need the formula for volume of a cube, which is 1/3 pi r squared times h. Let's plug in what we know. We know that volume is 1/3. I'm going to come over here. 1/3 times pi. We know that r is 1/3 of h, and we're going to square that. So if I simplify that, 1/3 squared is 1/9 times the 1/3 that was already in front is going to be 27, or 1/27. So I'm going to write that as pi over 27 times h to the 3rd power. Now that I've plugged in everything that's always true, I'm going to take the derivative with respect to time. So dv dt is going to equal pi over 27 is just a scalar, so 3h squared times dh dt. And this can simplify a little bit, so dv dt equals pi over 9 times h squared dh dt. And then at the moment that we care about, we know what h is and we know what dh dt. We want dh dt. So dv dt is 0.01. 0.01 is going to equal pi over 9 times h, which is 2 squared, times dh dt, which we're trying to find. So you can use a calculator and isolate the variable. You're really going to be plugging in 0.01 divided by 4 pi over 9. And again, leaving that answer in terms of pi is going to give you 9 over 400 pi, and our units here are inches per second. So your final answer as a sentence, which you should write, would be, at this moment, the height is changing at a rate of 9 over 400 pi inches per second. All right, I'm going to make some more room for number 5. This last one is a little bit tricky, and then we will work through it. So here we have a sphere. We know that the rate of change of the surface area is 14 pi, and at the moment that we care about, we know the surface area is 36 pi. We're being asked about the volume. So it seems like we're going to need to use a couple of formulas here. We're going to need to use the surface area formula, which for a sphere is 4 pi r squared. It also seems like we are going to need to use the volume formula, which is 4/3 pi r cubed. Now our ultimate goal is to find the volume. So if I take the derivative with respect to t over here, I'm going to get dv dt equals 4/3 times pi times 3r squared dr dt. And let's just clean this up a little bit. This is going to give me 4 pi r squared dr dt. My ultimate goal is to find this. The problem is I don't know what r is and I don't know what dr dt is. So let's go back over here. Is there a way we could find r? And there is. We know that the actual surface area at the moment we care about is 36 pi, and surface area is 4 pi r squared. So we can find r, which is going to be r squared is 9, so r is going to be 3. So we can plug 3 in here. dv dt equals 4 times pi times 3 squared. But we still don't know what dr dt is. So let's look at the surface area formula, and let's find the derivative with respect to t, because we haven't really used this 14 pi fact yet. So dsa dt is going to equal 8 times pi times r dr dt. Now we know at the moment that we care about, that formula works all the time, but at the moment we care about, the surface area, the rate of change of the surface area is 14 pi, and that's going to equal 8 times pi, and we just found r. R was 3 times dr dt. So now we can solve for dr dt, which was the one thing that we needed to find the volume, the rate of change of the volume. So this is going to be 14 pi over 24 pi, which is just equal to 7 over 12. So I'm going to take 7 over 12 and plug it in over here so that I can find the rate of change of the volume, which is going to be 4 times 9, 36 pi times 7 over 12. And this is just going to simplify to be 21 pi. So at the moment, the volume is changing at a rate of 21 pi, and our units here are cubic meters per hour. So big ideas to wrap up this lesson. Every time you're approaching a related rate problem, the very first thing that you should do is draw a picture and list off all of your given information. And I really like to do that off to the left-hand side of the problem so that anybody that's looking at it knows I started by identifying all this information. Then you need to find a formula that ties together what you're trying to figure out, the relationship between the variables that you have. Typically that's given to you in the problem. If you're talking about volume or surface area, or a ladder leaning up against a wall is going to create a right triangle. After you have that equation, you're going to plug in anything that you know is always true, and then you're going to take the derivative with respect to t. Once you have done that, you can specifically plug in things that are true at the moment that you care about to solve for the variable that's missing. Remember, anytime you're missing something you need to solve for the variable you're being asked for, look back at your given information and see if you can manipulate that to get the variable that's missing. Make sure your final answer has units and that you're writing it in a complete sentence that makes sense with context to the problem. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.